Now, part 5, lecture 2, basis vectors, covariant and contravariant basis vector. See? Now, I recommend you to study part 1, 2, 3, and 4 deeply, okay, to understand the sequence. Now, I'll define covariant is defined as the partial derivative of R with respect, I'll change here, with respect to the curvilinear coordinate CI. This is by definition. Now, you see, the left-hand side, I is free index, and also is covariant. By definition, you see a lower index, you just say is covariant. But there is a trick here. You see, this I over here is upper, but it is in the denominator. So I can define this here as covariant. So upper index in the denominator, they are upper indices in the denominator, they are covariant index. Okay? Now, you see another point. The left hand side, there is one free index, the covariant. The right hand side is one free index. Okay? They must match. Okay? So that's important. I lower index is covariant, which doesn't happen over here, because here is upper indices, but it is in the denominator. Okay? By convention. Now, that's a definition of the base vectors. So, another important point, this is a tangent vector. Okay? I will put over here. This over here is A1. You see, this I is equal 1. This is A2. This is A3. Attention now. You see, in the generalized coordinates, okay, the basis vectors in general, okay, in general, the basis vectors are not orthogonal. See, in general, okay, could be, okay, some particular case, okay. So this is the definition of covariant basis vector. But from part 4 to match to be a tensor, you see, I will define the dual. Attention now, okay? Define the dual basis vector as, attention now, A superscript I. Okay? This is completely different from this. Okay? Then I will show the relation between this basis vector, okay, a dual basis vector. This is called covectors, okay? Covectors. Okay? Now, you see, I must define this just that the tensor is a map. Okay? So I can define this, okay, according to the definition of tensor. Always remember that tensor is a map. See? Because this is a tensor theory. Look how interesting. I'll define AI. I'll put here A1, okay, just for you. Then for I is equal 1. A1 is defined as the cross product of A2, A3. Now, the denominator is this scalar. You see, the denominator is a mixed product. Look how interesting. You see, you go to part 1 and see all this derivation, okay? And in part 1, you see clearly there is derived there, okay? Now, in detail, that this here is the square root of G, okay? You see that. Okay, but let's fix on this definition. Look how interesting. You see this definition, you can see clearly that the dot product, now we don't talk about inner product. Well, inner product is just an abstract, okay, that we developed in part 4, okay? There is no error there. Here there is an error, okay? This arrow here is according to the curvilinear coordinates. You see? Now, I'll take the dot product with this. Look how it's easy to see. Now just see it. This is scalar, this is scalar. See, this is A1. So, I'll put there. This is equal 1. You see? Here is scalar, is mixed product. Mixed product. This is mixed product, so this 1. But A1 dot A2 is equal, doesn't matter if A1 is here or over there, okay? I'll write here. So this will be A2, in this case, dot A2 cross A3 divided by A1 dot A2 A3. Look, I just multiply A2, okay, in both sides over here. You see? This is A1, this is A1, okay? I just take the dot product between A1 dot A2. Now, you see, from the mixed problem, fixed in this there, this is a determinant which has two identical rows. So this will be 0. Oh, fantastic. Now, A1 dot A3. This will be A3 dot A2 A3. Now divide by A1 A2 cross A3. So you can look, this is also 0 because this determinant which has two identical rows, so also will be 0. Fantastic. You see, now what is important for you that there is no obligation of A1, A2, A3 to be orthogonal.